Good morning, friends. Welcome to online classes from MGBC Arts, Commerce and Science College, Mudde Bihar. Its Department of Chemistry, and myself, Professor UMARFAROOQ HALYAL. Today, I am going to take your class for BSc 5th Sem. In that, paper 2. So, in previous class, we already discussed regarding to alloys, and today we are going to discussing about abrasives. So in this class we are going to study what are abrasives, the types of abrasives, and manufacture and applications of the different types of abrasives. So let us start. Abrasives. An abrasive is a hard and tough substance having sharp edges. It cuts or wears away materials softer than itself. And important properties of abrasives are penetration, hardness, fracture resistance, and wear resistance. And now coming for types of abrasives, there are normally two types: natural and artificial abrasives. Natural means they are naturally occurred or obtained. They are obtained from nature. Natural abrasives are sandstone, emergy or corundum, diamond, garnet, quartz, etc. And when we coming for artificial or synthetic abrasives, they are manufactured to have well defined and controlled properties of hardness, roughness, and type of structure. Artificial synthetic abrasives are silicon carbide, aluminum oxide, and tungsten carbide, etc. So here some examples regarding to natural and manufactured abrasives. In natural abrasives, alginous stone, chalk, corundum, diamond, emery, garnet, pumice, quartz, sand, tripoli, zirconium silicate, cuttle, kieselguhr. These are the examples of natural abrasives. When we coming for the next type, man-made or manufactured abrasives, they are silicon carbide, aluminum oxide, synthetic diamond, rug, tin oxide, and also tungsten carbide, etc. Here some uses of natural abrasives. For example, alginous stone. This is we are using for fine grinding of tooth enamel and metal alloys. In our tooth enamel and metal alloys, we are using alginous stone. The next one, chalk. It is one of the paste. So this paste we are using to polish tooth enamel, gold foil, amalgam, and plastic materials. And the next one in the natural abrasives, that is corundum. So this corundum we are using in the grinding of metal alloys. And in the diamond we have two types: natural, that is super abrasive, and synthetic. So natural diamond we are mostly using on ceramic and resin based composite materials, and the synthetic diamond we are using for manufacture of diamond saws, wheels, burns, blocks, and polishing pastes. Emery, this is we are using, may be used for finishing metal alloys or acrylic resin materials. The next natural abrasives, that is garnet. This is we are using in grinding of metal alloys and acrylic resin materials. The next one, pumice, that is rubber bonded flour. This is we are using in polishing of tooth enamel, gold foil, dental amalgam and acrylic resins. Some another natural abrasives like quartz we are using for the primarily to finish metal alloys, and they may be also be used to grind dental enamel. Next, sand. This is using in applied under air pressure to remove refractory investment materials from base metal alloys castings, and they are also coated onto paper discs for grinding of metal alloys and acrylic resin materials. The next natural abrasive, that is triple I, that we are using in polishing metal alloys and some acrylic resin materials. And some zirconium silicate, cuttle, kieselguhr, these are also used in different types. Now we are moving for manufacture and applications of carborundum, or another name for this one is silicon carbide. So this silicon carbide is also known as carborundum. So it is a compound of silicon and carbon with the chemical formula SiC, and it occurs in nature as the extremely rare mineral moissanite. And this silicon carbide powder has been mass produced since 1893 for use as an abrasive, and grains of silicon carbide can be bonded together by sintering to form very hard ceramics that are widely used in applications. So when we coming for history or discovery of this carborundum, in the year 1891, Edward G. Exon produced a small amount of silicon carbide while conducting experiments with the aim of obtaining a hard material from the reaction of clay and carbon. He passed a strong electric current from a carbon electrode through a mixture of clay and coke contained in an iron bowl, which served as the second electrode. Exon recognized the abrasive value of the crystals obtained, had them analyzed, found the formula to be SiC, incorporated the Carborundum Company in the year September 1891, and filed application for patent on May 10, 1892. From this, the abrasive alundum or carborundum is obtained when he was started an experiment to get a hard material from the reaction of clay and carbon. When he passing the current for that carbon electrode that containing clay and coke or carbon. So by that time this carborundum or silicon carbide is obtained. This is the structure. So the silicon carbide exists in about 250 crystalline forms. The polymorphism of silicon carbide is characterized by a large family of similar crystalline structures called polytypes, And alpha silicon carbide is the most commonly encountered polymorphism. It is formed at temperatures greater than 1700 degrees Celsius and has a hexagonal crystal structure. As you see in this picture, the structure of the silicon carbide or carborundum is hexagonal crystal structure, and for this heating we have up to heat 1700 degrees Celsius. And the beta modification with a zinc blende crystal structure similar to diamond is formed at a temperature below 17 degree Celsius. So when we heat this silicon carbide at more than 1700 degrees Celsius, it has the structure of hexagonal structure, and that is alpha silicon carbide. But the same this silicon carbide, when we heating below 1700 degrees Celsius, it is having a similar to diamond shape, and that is beta silicon carbide. And we coming for properties of this silicon carbide. This pure silicon carbide is colorless. So when coming for the properties of silicon dioxide, silicon carbide, so these are the crystals, colorless crystals, and these are vary in color from very pale green to black depending upon the amount of included impurities. And suppose if having black and green silicon carbide, both with a shape of hexacrystals, the material is extremely hard and sharp with excellent chemical properties, and the hardness is between diamond and fused alumina, but the mechanism hardness is higher than fused alumina. The micro hardness is in the range of 2840 to 3320 kilogram per mm square, and the silicon carbide is sharp but fragile with good heat resistance, heat conductibility, can be antacid and anti-alkali, lower dilatably, and electric conductivity. And this silicon carbide is quite stable chemically. It is stable to acids, not reacting with fumic nitric acid, nor with boiling sulfuric, hydrochloric or hydrofluoric acid. So this silicon carbide is stable chemical. So it is stable to acids, and this is not reacting with fuming nitric acid, nor with boiling sulfuric or hydrochloric or hydrofluoric acid. And this silicon carbide dissociates in molten iron, and the silicon reacts with the metal oxides in the melt. So this reaction is of use in the metallurgy of iron and steel. So this silicon carbon has high hardness, high thermal consistency, very good resistance at high temperature, low thermal expansion, electric conductivity, and it is a good semiconductor. And this silicon carbide has a non-linear electrical resistance, and this silicon carbide has silicon and carbon as alloying additive. When we coming for the production, so the silicon carbide is made today in much same way as when it is invented in the year 1981. So it is having the same type of production steps when that is started from 1891. First, high purity quartz is mixed with a high quality of coke or anthracite in large electrical furnaces, and that furnaces are heating of about more than 2000 degrees Celsius according to the reaction, that is silicon dioxide plus 3 carbon, that gives us silicon carbide plus 2 carbon monoxide. So this process is an endothermic reaction requiring between 8000 to 10,000 kilowatt hour per ton of product. So the simplest manufacturing process is to combine silica, sand and carbon in an Axen graphite electric resistance furnace at high temperature between 1600 to 2500 degrees Celsius. This is the production method. And now we coming for the applications. So this silicon carbide forms natural crystals which are very hard, very abrasive and dissociate or sublimate at high temperatures. It is for those reasons that silicon carbide is used in the following applications. That is first one, abrasive industry. With good hardness, silicon carbide is the first choice or raw material for manufacturing abrasive pipe, pumping chamber, etc. Its abrasiveness is 5 to 20 times than that of cast iron and rubber. The next one, electronics. In the electronics field, this silicon carbide is a semiconductor in research and early mass production, providing advantages for fast, high temperature and or high voltage devices. First devices available were Schottky diodes, followed by the junction gate FETs and MOSFETs for high power switching. Bipolar transistors and thyristors are currently developed. And the silicon carbide is also used in making LEDs. And for the structural materials, this silicon carbide we are using like hard ceramics and also armor and ceramic plates in bulletproof vests. So this silicon carbide is used as support and shielding material in high temperature kilns such as for firing ceramics, glass fusing or glass casting. So this silicon carbide kiln shells are considerably lighter and more durable than traditional alumina shells. And some another typical silicon carbide uses like suction box covers, fixed and moving turbine components, seals, bearings, ball valve parts, hot gas flow liners, heat exchangers, semiconductor process equipment, jewelry, etc. So thank you for listening the class. This is regarding to manufacture and applications of silicon carbide. And next class we are going to discussing about manufacture of applications of aluminum or corundum and manufacture and applications of tungsten carbide. Please go follow up all these points and kindly watch this video up to the end. Don't miss to subscribing this YouTube channel, because if you subscribe you will get regular update of your class videos. And once again, thank you.